want to start with an example where we're ultimately comparing two means. It's taken from the book, chapter 10, number 14, but I actually want to change the problem a little bit to make it a little bit more interesting. I want to change the numbers, the sample sizes in particular that are given. You can see N1 is 61 and N2 is 61. Same sample sizes. That's not very interesting. Let's make them different sample sizes. Let's also make them smaller so that it's maybe a more typical kind of situation with smaller sample sizes. I'm going to make N1 be 15 and N2 be 20. Okay, and we'll just see what happens when we make those be 15 and 20. We'll keep the summary statistics, X1 bar, X2 bar, the same, as well as the variances, S1 squared and S2 squared. We'll let those be the same. So we're trying to decide whether or not to purchase a new handheld laser scanner for use in inventorying stock. Okay, that's not financial stock. That's stock in a company, I guess. That's in your actual inventory. Tests are conducted on the scanner currently in use and on a new scanner. And ultimately, what you're interested in is you're interested in comparing the means, right? How many codes can be scanned per second? You're wondering, is the new mean higher than the old mean? Is mu1, the new mean, population mean, higher than the old population mean, mu2? Look at that, X1 bar is certainly a lot bigger than X2 bar. The sample mean for the first sample is certainly a lot bigger than the sample mean for the second. Intuitively, that's some evidence that the new scanner is better than the old one. It can scan more barcodes per second. But the question always is it statistically significant evidence of that for the population means? Is mu1, is this statistically significant evidence that mu1 is greater than mu2? But it is also phrased in terms of wondering whether we should pool the sample variances or not, because in part A, you can see we're going to test the null hypothesis that the population variances are equal. At the alpha equals 0.2 level, that's kind of a high alpha. Okay, so let's go ahead and do what it says to do here. Again, I'm going to use different sample sizes to make it a little bit more interesting. Let's write down these numbers with those new sample sizes. So what do we have here? I said let N1 be 15 instead of 61. Let N2 be 20 instead of 61. But we will go ahead and use the means that are given. X1 bar, the observed sample mean is 40. And X2 bar, the observed sample mean for the second scanner is 29. For the variances, we've got S1 squared is 24.9. S2 squared is 22.7. Those variances are not too far apart. Probably for the variance test, we're not going to reject the null hypothesis. Yes, those sample variances are different, but if we give the null hypothesis that the population variances are equal, the benefit of the doubt, probably we're not going to reject it, is my guess here with the F statistic. Let's see what happens. So let's do that first. Part A. We're testing the null hypothesis that sigma 1 squared equals sigma 2 squared versus what's the alternative? It doesn't say, does it? It doesn't say you suspect that the variance for the new is bigger than the variance for old. So if it doesn't say, if it just says test, you should do a two-sided test. And when you compute the one-tailed p-value, you should double it, even though that's a little bit fishy to do because the F statistic distribution is not symmetric. You might say doubling the one-tailed p-value is not necessarily the best thing to do, but it's what people do anyway. So we'll go ahead and do it. Statistics is full of things where when people apply it, maybe technically they shouldn't, but they do it anyway. That's not necessarily always a good idea in general, right? In real life, but okay. So let's see what happens here. We have to compute the F statistic. In the abstract, we could call it capital F. is a ratio of two sample variances, where by convention, we put the bigger observed one on top and the smaller observed one on the bottom, which technically means you're thinking about it after the fact. You can see that based on these data, the bigger observed sample variance is the S1 squared compared to the S2 squared. So we'll put that one on top and this one on the bottom. And the degrees of freedom for this F statistic comes in a pair, one for the numerator and one for the denominator. Since S1 squared is in the numerator degrees of freedom is 15 minus 1, 14. And since S2 squared is in the denominator degrees of freedom is 20 minus 1, 19. So this is going to be an F sub 14 comma 19 statistic. What's its observed value? We could call that little f. Well, just do 24.9 divided by 22.7. If we were given the standard deviations instead of the variances, we'd want to square them before computing this ratio, or you could compute the ratio of the standard deviations and then square. Either way you do it, you get the same thing. And once again, this is not going to be a very extreme observed value. It's not going to be a lot bigger than 1. You can see this is going to be just slightly bigger than 1. About 1.097 approximately. Not real extreme. Probably the p-value is not real small. Going to be a fairly large p-value. We double it, it's going to get even larger. We're probably not going to reject the null. But if we want to be more certain or more precise about the p-value, we could ask, first of all, what is the one-tailed p-value? Write that as a one-tailed p-value. We're doing a two-tailed, so we'll double it. Is the probability that this particular F statistic, which I'll use as a capital F right here, is as extreme or more extreme as what we actually observe, greater than or equal to 1.097. That'll be the one-tailed p-value. That, in a graph, is going to be the area under an F distribution with 14 and 19 degrees of freedom to the right of 1.097. Where is it on the picture? I don't know for sure. Maybe here or something. I'm guessing it's going to be a fairly large area. 0.3, 0.4, that's my guess. Go to your distribution menu. Go down to FCDF. That'll calculate an area to the left. We want an area to the right. Put a 1.097 here. 14 degrees of freedom for the numerator. 19 degrees of freedom for the denominator. This should be slightly bigger than 0.5. 0.583. 1 minus that is the one-tailed p-value we're after. This is approximately then 0.42, say. And therefore, the two-tailed p-value is going to be approximately double that. 0.84. Way, way too big to reject the null, like we suspected. Do not reject the null. We do not have strong evidence against the assumption that the null is true. Now, again, it's kind of funny. Technically speaking, especially when you write the alternative as a not equal to, technically speaking, you might say there's no chance the null hypothesis is exactly true, right? There's pretty much, if you're going to talk about it with probability, you could say there's no chance they're exactly equal. But that's not the point. You're missing the point if you think of it that way. The point is to give the null hypothesis the benefit of the doubt and only reject it if you've got strong evidence against it. And then as a practical matter, if they're exactly equal or just slightly different, it doesn't make much of a difference anyway as far as applying the ideas, applying the model that we use. By the way, this statistic having an F distribution, if you look in the book, is based on the assumption that the null is true, that these variances are equal. That is what guarantees this has officially what's called an F distribution. Okay, so what's the conclusion here? The conclusion is, yeah, even at the 0.2 level, we're not going to reject the null. Therefore, we say pooling is appropriate. Maybe that makes us happy, especially in the olden days. That makes you happy because then you didn't have to worry about Smith-Satterthwaite degrees of freedom. They didn't have calculators and spreadsheets and so forth back then, and they'd want to make sure pooling is appropriate. So I would think more typically they'd want to use a smaller alpha, but in the book we used this big alpha. Now go ahead and finish the problem. We're going to pool to compare the means now. So in part B, it says compute the pooled variance. The formula is n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared all over n1 plus n2 minus 2, which is the sums of those 2 degrees of freedoms. And that quantity, n1 plus n2 minus 2, is the degrees of freedom that we'll use to compute the confidence interval as well. So with my new n1 and n2, that's not the same as in the book. 15 and 20, what does this become? 14 times s1 squared is 24.9 plus 19 times s2 squared is 22.7 divided by 15 plus 20 minus 2, which of course is 33. Yep, it's a sum of those two, 14 and 19 as well. Compute this now. 14 times 24.9 plus 19 times 22.7. 779.9 divided by 33. 23.63, repeating, for the pooled proportion. It is in between the other two, or pooled variance. It is between the other two variances. It is a sort of a weighted average of those two, with more weight being given to the smaller one in this case, because that goes with the bigger sample size. That number is a little bit closer to this number than it is to that number. And that's what we use now to compute the confidence interval to estimate the difference between mu1 and mu2, which is what part C is about. You can see it says find a 90% confidence interval on mu1 minus mu2. The formula is x1 bar minus x2 bar plus or minus t, right? With means, use t as your special multiplier of your standard error. In general, the standard error is square root of s1 squared over n1 plus s2 squared over n2. But in the case where you pool, s1 squared and s2 squared gets replaced by the pooled variance. It can be factored out and square rooted to become, when you pool, when you're doing pooling, x1 bar minus x2 bar plus or minus t sub alpha over 2 times the pooled standard deviation, because we took the square root of the variance, times the square root of 1 over n1 plus 1 over n2. I factored it out and took the square root after making the replacement. I replaced s1 squared and s2 squared with sp squared. So you could argue it gives you a little simpler formula, slightly. You could also argue it's more accurate based on the degrees of freedom if indeed the population variances are truly equal, or really close to equal at least. Now plug in the numbers. x1 bar is 40, x2 bar is 29. 40 minus 29. Plus or minus, what's alpha in this problem? Alpha for a 90% confidence interval, that's what we're after, is 0.1. Alpha is 0.1, so alpha over 2 is 0.05. Degrees of freedom is n1 plus n2 minus 2 is 33. So T sub 0.05 based on 33 degrees of freedom, what's that going to be? Z sub 0.05 is 1.645. T should be a bit bigger, right? Because you need a little bit more cushion when you use the T distribution. Inv T will do it for us. Subscript is an area to the right. This is a CDF, so I need a 0.95. 33 degrees of freedom should be a bit bigger than 1.645. 1.692. Okay. Higher the degrees of freedom, the closer it gets to 1.645. Just to illustrate, if I made this 500 or something, it should be pretty close to 1.645. Yeah. So that goes in there, 1.692. Pooled standard deviation is going to be the square root of 23.63 repeating. 23.63333 to the 0.5 power. There is the pooled standard deviation, about 4.861. Square root of 1 over n1, 1/15th, plus 1 over n2, 1/20th. So we get 11 plus or minus what? (1/15th) plus 1/20th. Take the square root, multiply by 1.692 and also 4.861. Our margin of error is pretty close to 2.8. In interval notation, that would go from 8.2 to 13.8. What does it mean? We're pretty confident, we're 90% confident that the true mean difference mu1 minus mu2 is in there. In other words, we're very confident it's positive. If you did a 95% confidence interval, the interval would be bigger, but I'm sure it would still only contain positive numbers. Probably even a 99% confidence interval would only contain positive numbers. So we're very confident that mu1 is bigger than mu2. Did I do an official hypothesis test at the 10% level of significance? Not really, unless I think of the alternative hypothesis as two-tailed. The two-tailed p-value, the fact that these are all positive numbers would mean the two-tailed p-value is definitely less than 0.1. We would definitely reject the null. We definitely, at that level, have strong evidence against the null. You only can do hypothesis tests with confidence intervals if it's a two-tailed test to be technically correct in matching the value of alpha. But again, this is so far away from zero. I'm sure, again, a 95% and a 99% confidence interval, even though they'd be bigger, in all likelihood would still only contain positive numbers. The p-value for a two-tailed test, I'm sure, is very small. Does the problem actually ask us to do the test? Not officially, no. But we sort of are doing it answering part D there. Does the new laser appear to read more barcodes per second than the old one? I think is what they mean than the average. And the answer would be yes, because our confidence interval only contains positive numbers. Part E, since the number of barcodes that it can be scanned is discrete, we have not really satisfied the normality requirement of the T distribution test or the T interval test. What theorem justifies the use of pooled T procedure in this case? Actually, I'm not sure that we have a theorem that really officially justifies that in the sense that we're going from discrete to continuous. I mean, in general, the central limit theorem implies X bar is approximately normal. I think that is enough to justify the pooled T procedure. Yeah, technically speaking, this theorem that's right on page 344, right here, does assume these are independent random samples drawn from normal distributions. The central limit theorem says the sample means are approximately normal when the sample sizes are large enough. I think that is what the book is getting at, though it's not clear exactly how you say, because of the central limit theorem implying the sample means are approximately normal, we can therefore use this theorem. Because this is talking about independent random samples of normal distributions from the original populations, not the sample means. So I think that's what the authors are getting at, but it's not really a precise kind of application of the central limit theorem in that sense. So I think I probably would not ask a question like part E on the exam, at least. If we were to try to use the table for the F statistic test that we did, how would you go about doing it? Could you compute this one-tailed p-value without a calculator? Not so precisely. So what could you do? You could maybe see it's bigger than 0.1. Going back to one of the F tables, 14 degrees of freedom for the numerator and 19 degrees of freedom for the denominator. Remember, it comes in two sets of pages here, one with a 0.9 there and another set of pages with a 0.95. That 0.9 is labeling the area to the left. It's a CDF value. Degrees of freedom for the numerators across the top. Degrees of freedom for the denominators across the side. We're looking for 14 degrees of freedom for the numerator and 19 degrees of freedom for the denominator. Now, what we see here is the number 1.878. What is that telling you? That 1.878 is referring to the critical value on the horizontal axis that makes this area 0.9. 1.878. We could confirm it with the calculator. Go back to the F distribution here. FCDF. 1.878. 14 degrees for the numerator, 19 degrees of freedom for the denominator. We should get close to 0.9 here. Yeah. Meaning the area to the right is close to 0.1. Our critical value, 1.097, is not as extreme as 1.878. So our one-tailed p-value is bigger than 0.1, and our two-tailed p-value is bigger than 0.2. More precisely, it was close. One-tailed was close to 0.42, and the two-tailed was close to 0.84. Either way you do it, it's bigger than 0.2. You do not reject the null. If we had not pooled the variances, would we have gotten a much different answer? Let's experiment and see. So go to my stat menu, go to tests. I am interested in doing the confidence intervals here is what I'm interested in doing. Two sample, not t-test, but two sample t-interval. It's assumed there that it's for means, a difference of two means. Set of data this time, let's do stats. Plug in the numbers. X1 bar was 40. S1 square, S1 is the square root of 24.9. The variance was 24.9, and the calculator had to do its square root, 24.9 to the 0.5 power. Close to 5. N1 for us was 15. X2 bar was 29. Sample standard deviation for sample 2 is a square root of 22.7. And N2 was 20. Confidence level was after 90%. Do we pool or not? Well, let's do it on yes first and see that we get the same answer, hopefully. Calculate. 8.8. Yep, there we go. 8.2 to 13.8. Got the same answer when we pooled. Degrees of freedom is 33. 15 plus 20 to minus 2. What would we get if we don't pool? Let's try it out. Hopefully it's not too much different. Is it going to be bigger or smaller for the confidence interval? It depends on what the degrees of freedom ends up being, I think. It's not just based on the degrees of freedom, though, because you use this formula instead of this form. This one instead of this one. And so the S1 squared and S2 squared are used individually instead of pooling. So it's not just based on a difference in the degrees of freedom resulting in a different T. It's also based on the fact that this could be slightly different than this. It's hard to say for sure ahead of time, I think, if it's going to be bigger or smaller. Let's not pool. Do I have a guess? I have a guess that maybe the degrees of freedom will be smaller. And in all likelihood, the confidence interval will be a bit bigger because it'll be conservative. But I could be wrong. Yeah, degrees of freedom was a bit smaller. It went from 33 to 29.52. I do believe Smith's Satterthwaite would give you the same thing, though I didn't take the time to double check it. But again, these numbers are used instead of the pooled standard deviation. The interval is a little bit bigger. It still rounds to the same thing. But I believe it was before it was 8.18 and 13.81 or 82 or something. So it's ever so slightly bigger, but it does round to the same answer to one decimal place. Okay. But there could be examples where the differences are a little bit more extreme. Can I clarify anything? If we do the hypothesis test, again, the test statistic is a T statistic. It would be x1 bar minus x2 bar in general divided by square root of s1 squared over n1 plus s2 squared over n2. But when you pool, for pooling, you could sort of simplify the bottom to the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. When you pool, you'd use n1 plus n2 minus 2 degrees of freedom. If you don't pool, use Smith's Satterthwaite, or more likely use your technology. Unlike math, there are debates in statistics. Debates about best methods. And the best method is not always clear. Okay. They are based on different mathematical models, different assumptions, but different people might have different, argue that different assumptions are appropriate in different circumstances. There's also like, should your estimator, does it have to be unbiased or not? S squared is unbiased for sigma squared, but S is not unbiased for sigma. You remember that? So is it good to use S, the sample standard deviation, to estimate sigma, the population standard deviation, even though it's not unbiased? Could you make an unbiased estimator? You actually can. But is that necessary? Is that best? There's debate. People have different opinions. That happens in statistics. And people also, again, have different opinions about the value of p-values. You can Google it, search for p-value debates or something like that. People have very strong opinions about how much p-value should be used. especially in drawing conclusions and especially in deciding whether a scientific paper should be published or not. There's sort of this magical 5% standard, but why? Why 5%? Why not 10%? Why not 1%? In reality, what really goes on when people do statistical studies and they get p-values is it's just one piece of evidence. It's not the end of the story. To me, that's the main lesson.